So in biology 1, a long time ago, you learned about cellular respiration in a little bit of detail. Probably not a ton. We get to learn about it in a lot of detail now. So what's the point of cellular respiration? To make what? Anybody know? To make, we don't say to make energy. Why don't we say that? Energy cannot be created nor destroyed. We are converting chemical energy, I'm sorry, I'm looking for my point. Chemical energy of food into ATP. So the point is to make ATP. Where the heck did I put it? It's maybe an energetic. Here it is. Yeah. Okay, so a couple of review slides. Energy is stored in organic molecules. We know this. Okay, carbohydrates, fats, proteins are the main ones used for cellular respiration. You can use nucleic acids, but they're not used so much. So we know what heterotrophs are. These are organisms that have to eat food to get these organic compounds. They undergo catabolism, or break them down to get raw materials for building other macromolecules. But they also use it for catabolism to produce ATP. So cellular respiration is the process of catabolizing these organic compounds to eventually produce ATP. I'll put in quotes, burning of fuel. Okay, it's not really burning, but it's a slow release of energy, and it's catalyzed by many different proteins. It's a sort of long, arduous process. There's lots of different enzymes involved in many steps. If you release all the energy at one time, you would like all your cells would just come up. So it's a slow release of energy. See that little boy with the ice cream cone. And this morning, okay, so yesterday my mother-in-law picked up Marie, the little one, took her home and like made Halloween cookies with her and brought them home yesterday, and they all had one. Some of them have icing on them. Anyways, this morning, I left the cookies like on the counter. They're in this big container. The little Fletch like snuck 3 of them. At one point I saw like little icing on his cheek. I was like, buddy, what are you doing? He's like, so I had to move them, like, they're too tall now. I have to like move them to the back. I'm gonna put them away. Thing. Anyway. He told Fletcher, he told my husband, he like made him come to like the side of the stairs where I couldn't see him. Oh, today they could wear their costumes to school. And he's Spider-Man. He's like running around the house this morning. I'm so sad. I should have taken pictures. I'll have to show you Monday. But I didn't, after Halloween. Anyway. Okay. About 75% of the ATP you make goes into just keeping you alive right now. Okay? So housekeeping things like allowing your body to just your cells undergo regular work, DNA synthesis, protein synthesis, your little organelles moving, your little vesicles moving in your cell, stuff like that. So just that stuff most of it's used for just maintaining life. So when I used to teach biology 1, I think one of the test questions I had was basically like, why would you die if you just sat on a couch and did nothing for like weeks on end and drank water, but why you would eventually die if you didn't have any food? And it's because, even though you're not expending any energy by like moving around, you're still expending energy, your body is, right? Your heart's beating, you're breathing, like physically respiring, breathing, and all this other stuff is going on. So most of the ATP you use is just to keep you alive. And if you're pregnant, even more of it's used to, help the baby, provide baby nutrition and stuff like that. So about 25% of it goes into allowing you to do your activities. And this is just interesting. I don't know, I put this in here a long time ago, but the more active you are, physically active, the more energy you need, so you don't, waste away to nothing. This thing is just kind of interesting. So this says kilocalories consumed per hour by a person that is 67.5 kilograms, which is 150 pounds. If you go to like Europe and stuff, they measure your weight in like kilograms. Weird, like the gym I go to, we have kettlebells and they're all in kilograms. And now I'm sort of, when I first started going, I was like, 12 kilograms, I'm going to die. And now I'm like used to it, and I think like it's a lot. Like 12 kilograms is actually kind of a lot. I don't think anyway. Which is why I'm really slow right now. But I did all these lunges yesterday with like 12 kilogram kettlebells in my hand. I did like, I don't even know how many, 200. Anyway, ridiculous. Ridiculous. Anyways, some people are like, I'm real competitive. So walking 4 miles an hour, which is a pretty fast pace, 231 kilocalories per hour. Let's see, what are some of the stuff people doing here? Running. Here we go. 7-minute miles. That's pretty fast. 865 calories an hour. What else is on here? Dancing. Lisa's a dancer. Dancing's a lot depending on what you're doing. Driving a car. You all do that. Eating. Anyways, okay. All right. We've already talked about calories. I don't really need to talk about that, but remember, it's just energy. We've talked about food labels a long time ago. I don't need to go into that. But remember, like 90 calories is the big C, kilocalories. So
I saw that.
You find funny stuff when you Google words. Okay. So the model we talk about when we talk about cellular respiration, we use glucose. Glucose is what we call the model because glucose starts at the very beginning and goes all the way through every single step to the end. Now your body can metabolize other organic compounds like I said, other carbohydrates and lipids and proteins. So they have to be modified and they might actually enter in different parts. They don't start at the very beginning necessarily. So we talk about glucose being the model. At the end of this chapter, we'll talk about the other ones and kind of where they fit into the whole process. So cellular respiration is a slow catabolism of glucose eventually to produce ATP. This is the equation for cellular respiration you need to know. You should know it already from Biology 1. If you don't, you need to remember it. Really, the equation you need to know is the one on the bottom there. But it's glucose, C6H12O6 plus oxygen produces energy in the form of ATP, some water, and carbon dioxide. Now, there's another waste product that's not on there. What is it? Who said it? I heard something. Heat. Yes. You are right. Heat. So ATP is utilized. The water, we say it's a waste product, but water is just water. But the carbon dioxide will diffuse out of the cell, and the heat will dissipate as well. We talked about the fact that we're endotherms. We use our metabolism to keep our internal temperature what it is. So we use that heat to keep your own body temperature. Now, when you do something more physically active, like running or whatever, you're going to get hotter, your internal body temperature goes beyond maybe what needs to be, so then you'll try to cool yourself down. But, all right, so I mentioned before combustion, cellulose has a lot of energy. When you light it on fire and it just burns, it releases a lot of energy all at one time. Okay, we can't do that in our cells because they would all self-ignite. So cellular respiration is the same kind of thing, but it's a slow release of energy. Many, many steps, many different enzymes, and all that energy is eventually converted to ATP. Just like the combustion of fuels needs oxygen, we need oxygen for cellular respiration. We say oxygen is the final electronic separator. Did you learn that Biology 1? You did. Yes, I should say, so you remember that.
We left that light up all the time. Yeah, he really did. He loves like no, we haven't nothing on our own too. Just like we're all together.
Well, it is the final electron acceptor. What does that really mean? We'll talk about it a little bit later. And there's a lot of enzymes involved. Electron acceptor. Sure. If you don't understand what I'm saying, if I'm talking too fast, stop. Acceptor.
Oh, I know, I was thinking.
Okay.
I knew the acceptor of the item.
Okay. Okay. Oh, I added this a couple years ago for I don't even know who. But anyways, so what do cells do with glucose? A lot of it, like I said, is used for production of ATP. Some of it is used as building blocks for other organic compounds. Okay. Or you can store your extra glucose, right, as glycogen in your liver and your muscle cells. We talked about that, yeah? Or if your glycogen stores are full, you can store them as fat, so triglycerides. That's what you do with your glucose. All right, so cellular respiration is not very efficient. Just like I think I talked about before, your car. If you drive once, I live in Blackwood, and when I get in my car here, you live in Blackwood, right? Yeah. So if you drive here, you're not going to touch your engine. Okay, it's going to be really hot. Your engines in your car are not very efficient. A lot of the energy is lost for friction. So we are not very efficient. Only about 40% of the energy in the glucose is captured. The rest of it, 60% is lost as heat energy. Anyway. Okay, so how do we harvest energy from fuels? So large molecules are slowly broken down or catabolized. What really happens is, what really important is the breaking of bonds and the moving of electrons. High energy electrons. They're like my children. They're taking them. Electrons are like toddlers, okay? These high energy electrons are what matters. And they're like my kids. Like, they have a lot of energy. They just run. And like, my children woke up at 5:15 this morning. So they were so excited they got to wear their costumes at school today. I kept being like, go back to them? No, it's not so cute.
Who was like that? I remember that was wake up.
They just show up in your room, like right next to your bed.
I used to do the same thing with my parents.
I might go away.
Everyone's a heart attack right there. I wake up and a kid is
I can hear them open their door.
It's so funny. It's all like when my parents are asleep sometimes, like I'm running to their room, like jump on their. I do that. I love my parents. Like, good morning, y'all. So where's breakfast? When I was little, I couldn't like get up on the bed. I would like go next to my parents' bed, and my dad, like sometimes his arms would be like on the side of the bed. I would just like shake it. I was like, Daddy. He tells this story every time. Like a beaver so annoying. Oh. He was like, I had to go get your milk, and then I'd turn the TV on, and then I was like. And I would just
That's awesome.
I remember one time I lost my tooth on a white road, my first tooth, and like I just like it was like 4 a.m. I don't even know why
You couldn't find it.
And I ran into my parents who was like, "Y'all, I love tooth," and they were looking at me like, "Go back." What are you doing? Yo, what are you doing over here? Because like I went to I looked, there's like a big black hole, and I was like. It just like flew out of my mouth. Wow, you hard. Like I was like, I lost my finger. I was on the run. It just like came out of my
Oh man. Okay. Anyway. Children. Okay. So just like toddlers, electrons, these high energy electrons, they have a lot of energy. When they move, they carry their energy with them. And the cell's going to use that to do work. Okay, the energy is usually stored in another bond. Or some of that energy is lost as heat. or some of it's used to make ATP, and I'll talk about how that is, but that's, well, we'll talk about it. All right, so we're going to talk about LEOGR. I've talked about that in here already, haven't I? Leo, the line goes, yeah, I don't remember what it was. Well, let's try it on.
Lost electrons?
Yeah.
Yeah, I did.
All right, oxidation and reduction. So the loss of electrons is oxidation. So something that loses electrons has become oxidized. The gain of electrons is reduction. Something that gains electrons, we say, is reduced. You learned this in chemistry, yeah? You learned in physical science. Physical science is probably going to go away.
I think I
have no idea what's
I read it.
going on.
I was reading that and writing an email.
Alright, so the yellow ball is like a molecule. The yellow ball loses an electron. The electron is gained by the blue ball. Which one is oxidized? The yellow or the blue? Which one is the yellow is oxidized, the blue is reduced. Reduced. Right. So usually something that loses an electron becomes an anion. It's negatively charged, yeah? Okay. I mean positively charged, what am I saying? Cation. Something that gains an electron in my head. It has an extra negative charge and it becomes negatively charged. We'll talk about that. Anyway, oxidize, reduce. There we go. Oxidation reduction reactions are always coupled. They occur together. If something loses an electron, it has to go somewhere. So oxidation and reduction always happen together. Okay? Cell respiration is a series of oxidation reduction reactions. Something gets oxidized, something gets reduced, and it happens again and again and again and again. Same thing with photosynthesis, really. They're both oxidation reduction processes. We also call them redox reactions, if you've heard that before. Questions so far? You're good? Okay. The thing with electrons, just like my kids, okay, they can't travel alone. All right. If I told my kids, like, peace out, go to school in the morning, and then go, like, I would never do that. Okay. They would get lost. They would get scared. They would do whatever. The electrons can't travel by themselves. They have to have, like, a chaperone. Okay. A little parent or somebody to hold their hand and take them to where they need to go. Okay. So the parent or the little chaperone for electrons is actually a hydrogen atom. Electrons themselves travel with a hydrogen atom as part of a hydrogen atom. Hydrogen atoms are called protons. They have one electron. So when a hydrogen moves, it takes its little electron with it. It takes its little high energy electron with it. This little toddler. So in cells, when you move hydrogens, you're moving electrons.
This is like from one atom.
From one like molecule to another. Yeah. So if we apply this to our equation for cell respiration down here. So look on the left side. Okay, we have glucose that has a lot of our hydrogen atoms. Those have our electrons we hear about, the toddlers that are super high energy, okay? So in the process of cell respiration, if we like use this knowledge we talked about here to apply it down here, what gets oxidized in cell respiration? What loses electrons? The glucose. Okay, and where do they end up? With the oxygen to make water. And the leftover of the glucose is the CO2. Okay? Go ahead.
So they can only occur, like they can only happen if one of these reactions has hydrogen.
Yeah. So the process of cell respiration, the glucose is oxidized slowly, and the oxygen is reduced. The final electron acceptor, all the electrons end up with the oxygen to make water. Yep. Yeah. Yeah. Okay, well, okay. I say slowly, but in reality, it's really, really fast. It's slower than like regular combustion, like lighting something on fire. It's slower than that, but it's not really slow. Okay. Alright, so we say that the process of cell respiration, the glucose has been fully oxidized when it's over because there's no more hydrogen, therefore there's no more electrons that can travel. CO2 is a fully oxidized molecule, it's a waste product, just diffuses out of the cell. Okay, now a long time ago I talked about electronegativity, right? That's the attraction an atom has to an electron, yeah? The most electronegative atom we talk about in biology is oxygen. Oxygen is the final electron acceptor. It sort of makes sense that it's the final electron acceptor because it really has a huge affinity for attracting electrons to it. Supposed to be an O2. I don't know why the 2's down there. So oxygen gains all those electrons and becomes water. We say that water is fully reduced. Sound good? You might check and see if this is in the Dropbox. Okay, yeah. I change these every year, but okay, I'm talking about all this. All right, so also something else we're going to talk. This is like in my introductory PowerPoint. There's like 4 for this chapter, or 5. There's one on glycolysis, Krebs. There's 5. Yeah. So the electron transport and then fermentation. So this is the first one. That's 5. Anyway, so electrons and hydrogens, like I wouldn't want to take my kids to school from Blythewood by on foot. Okay, I need to get in my car. All right. So just like that, okay, the electrons and the hydrogens, in order to move around the cell, need to have like a shuttle bus to hop on. So these shuttle buses are what we call electron carriers. Electron carriers themselves. Whoa, I lost my egg. Okay, throwing it away. These are like the shuttle buses. All right, so there's 2 electron carriers we're going to talk about in cell respiration. One is called NAD plus. What does the plus indicate? It's already lost an electron. Yep. So NAD plus actually carries 2 electrons when it's reduced in the form of NADH. Okay, 1 electron fills that positive deficit to make it then neutral, NAD period, and then 1 comes with a hydrogen atom. We'll talk about that later. But so NAD plus is a fully oxidized electron carrier. When its little bus is full, it's an ADH and has 2 electrons it's carrying. NAD plus carries really, really high energy electrons. Okay, like my kids. The FAD really should be the FAD. But the FAD carries lower energy electrons. These would be like 10-year-olds maybe. And when it's fully reduced, it's FADH2. No, I need to delete the 2 plus. It's really just FAD. Yeah. But the FAD electrons are lower energy. That'll become important a little bit later. Don't need it. These are really complicated looking molecules. You don't need to know them really. It carries 2 because it has 2 hydrogens when it's fully reduced. Another analogy would be like money in the bank. Okay, and they can convert back and forth, and they do. They're like, you know, my car, when I drop my kids off, I drop my little electrons off. You know, my car doesn't change. I can go pick them back up. I think about like little electrons. All right, so cell respiration has 4 stages, depending on how you talk about it. You probably learned maybe 3 in Bio 1, but there's really kind of a 4th one-ish. So the first one is common to both anaerobic and aerobic respiration, and it is glycolysis. We say it's anaerobic because glycolysis occurs in the cytosol. It does not require oxygen at all. Glyco means sugar, lysis means splitting. Glycolysis is the initial splitting of the glucose. We'll talk about it on Tuesday. We'll talk about it on Monday. I keep Mondays wrong.
Wait, is those put on Monday?
Yeah, because their lab reports due Monday. I don't really want to make you. Oh yeah, they're in 3rd. I just moved that for last time. Sorry. Can't do that. Somebody who said the other day that like the universe doesn't want us to learn. Was that you, Jackson? Doesn't want us to learn APIs?
Okay, yeah.
I don't think they do because next week I have a senior meeting. Monday's ed ops, and that's part of this class. So next week's kind of weird. The week after that, Veterans Day Assembly on Tuesday, pep rally on the 13th. The week after that, I'll be gone 2 days, and so some of y'all will be in Boston. The week after that, is Thanksgiving. The week after that, there's the blood drive on Friday. The week after that's Winter Day. It's like.
Oh, yeah.
All right. Anyway, I want to finish this PowerPoint anyways. Me too. Aerobic respiration are the others. It's using oxygen, and the following stages I'm going to talk about can only happen if oxygen is available. So it happens in the mitochondria, and there's 3 of them. Pyruvate oxidation, which they don't even show one here. Oxidation is losing electrons, so pyruvate is oxidized. We'll talk about what that means. The Krebs cycle and the electron transport chain. The Krebs cycle is also known as the citric acid cycle, if you learned that in Bio 1. But, so there's 4 stages to aerobic cell respiration: glycolysis, pyruvate oxidation, Krebs cycle, electron transport chain. Glycolysis by itself does not require oxygen and can actually, in fact, occur when there is no oxygen present. The rest of those occur in the mitochondria itself. Okay, and that's the end of our first little PowerPoint. I know, really. Okay.
Yeah.